Okay. Okay, so on Monday, we were talking about reductions, right? The sodium, the lithium reagent, which one's strong, which one's weak. Now, let's just do a quick recap with the next practice problems in here. So this time, you guys are going to tell me what kind of reagent can we use to reduce the following molecules. Okay, so let's start with the first one, which we actually did it already. We have, what's the functional group in here? What's the name? It's an ester. So what can I reduce it with? What about the sodium reagent? It's not going to work. Exactly. Only the lithium reagent. And what was the reason behind that? It's not that very reactive, exactly. Now, next one, what do we have? We have two different ones, the sodium and the lithium reagent. The sodium reagent, that's the weak reducing agent. So that one can only react with carbonyls that are very reactive, like aldehydes and ketones. But the lithium reagent, that guy is very strong. So it's going to be able to reduce every single carbonyl that you presented with. Say that again. Aldehyde and ketones. Okay. So in that cyclic ketone, what can I use? Both, exactly. NABH4 or the lithium reagent. The next one, we still have a ketone, so that means that I can also use both the lithium or the sodium reagent. And then what about this one, last one? Just lithium. So yeah, as long as you're able to identify your reagents and what they're gonna cause, you guys should be pretty good. Question? Yes, it is gonna be preferred. But either way, now, let's look at a question that you're more likely gonna get on the exam, which is the following one. In here, you're given a synthesis of something now, and you are asked for the reagents. You have either the sodium reagent, the lithium reagent, or both. You have to identify it. Okay, I have one vote for both. What do we think? Both as well? Both of them? Be careful. It's actually just A. But let's see why. So hopefully you guys saw the most obvious one. What functional group is that? Ketone. Okay, beautiful. What's the other carbonyl that I have? CO2, right there. We can see that part is preserved. The only one that's changing is my ketone. So remember, if I were to change my ester for an alcohol, that means that I need to use the lithium reagent because that's the only one that can do that job. But in this case, if I'm maintaining that, and if I'm only working with a ketone, that means that the only possible one is going to be the sodium reagent. Yes.
So does that mean if you were to use both of them?
If you use both at the same time, then yeah, both of them are going to be affected. We don't understand? It's not going to be both. Yes. But yeah, most of the times you're not gonna ever use both. So basically it's just a distractor in there. Again, you have to see what's being changed. If you start with a ketone in here and an ester, okay, we have to see if they're changing in the product. We can see that we're going from a ketone to a secondary alcohol, and then I still keep that ester. I'm only changing one of the aspects in the molecule. The only one that can react just with the ketone is going to be the sodium reagent. That's why it's just A. It's not going to be both. There you go. It's just going to be this one because ketone is very reactive. Now, ester, if we were to change it, then we need something stronger like lithium. In this case, that didn't happen, so we're not going to use that one. Okay, any questions on normal reductions? Pretty simple. Do we see the pattern? We're good? Do we have a question here? Okay, it seems like no. Okay, now, the next type of reductions that you have to know is Grignards, which he talked about in lecture today, right? Okay, what does Grignards do? How does it look like? MGS? X? Yeah, it can be chlorine, bromine, any halogens. Okay, what else? What else do you know about Grignards from lecture? There's 2 steps, sometimes, yeah. You're on the right track. Okay, yeah. Say it again. There you go. Yes. Okay, so we do have a pretty okay background with Grignard, so let's just start talking about it. So, like you mentioned, it's going to be whenever you see magnesium with some sort of halogen together. Now, more specifically, your Grignard reagent is going to be a carbon chain that has magnesium and bromine. Okay, that's how your Grignard reagent is going to look like. Now, that's not going to be the active one, because to make it active, magnesium and whatever halogen you have, they are basically going to go away, and that's going to leave you with the actual nucleophilic species, which is just going to be a pure carbon chain. Okay, now it's the same thing that we were talking about with the sodium and lithium reagent. With those guys, it was just a hydride ion, a hydrogen with a negative charge. This time it's going to be a carbon chain with a negative charge. Okay, that's the main difference between them. Now, as you can see, if we have a carbon chain with a lone pair and a negative charge, that's going to be a good nucleophile, and that's also going to be considered a good base. Now, let's quickly review our differences between nucleophiles and bases. What do nucleophiles do? They attack, and remember, they get connected in the molecule, so we're making new bonds. Makes new bonds. Then what about bases? What's the role of bases? They break bonds. Specifically, they always take a hydrogen. They always take a proton. Take a hydrogen. There we go. And then this one, I already gave it to you guys. It's going to be both a strong nucleophile and a strong base. Now, since it's going to be both a nucleophile and a base, for a nucleophile, that means that you would follow a reduction, okay? But if the Grignard reagent acts like a base, you're not going to do a reduction. You're just going to do your simple acid-base reaction, which is what we have to answer next. Grignard is going to act as a base whenever there's an acidic proton in the molecule. So let's just write this here. Whenever there's like OH, exactly. So yeah, the most common example that you're going to see is going to be an OH group, an alcohol group. Simple as that. So far, questions on that? It should be pretty straightforward if you paid attention in lecture. Pretty easy? Okay. Now, before we even talk about the actual reductions, sometimes you're going to get a multi-step problem in where you first have to make your Grignard reagent. So to do that, first of all, you are going to start with a molecule that has a carbon chain and a halogen. Do you guys remember the name for that functional group? Alkyl halide, beautiful. This guy is just your alkyl halide. And then you need magnesium in ether. Specifically, it has to be in ether because this guy is going to be an inner solvent, meaning that it's not going to be reactive, so everything's going to be stable, and we're always going to get this product. Okay, but again, remember that at the end, magnesium and bromine go away, and you're left with the active nucleophilic species. Okay, so far, questions on the concepts? Pretty good? Make sense? Okay. Yes, the carbon chain with the lone pair and the negative charge in there. Now, as you can see, you have a little picture in there with a little duck. Now, the duck, under it, it has aldehydes, ketones, esters, and other functional groups that you don't have to worry about. But again, main focus is that none of those carbonyls have some sort of acidic proton. The only one that's on the side is your carboxylic acid. Why would carboxylic acid be on the side? Because it has an acidic proton, exactly. So we're not going to be able to do a normal reduction in that case. Okay. Now, let's look at the actual mechanism. Now, again, if we're doing our reductions, we know what's going to be our electrophile and what's going to be the nucleophile, right? What's going to be the electrophile? Electrophile, not nucleophile. Remember that we were talking about a dipole moment? Partial positive in the carbon, that's my electrophile, partial negative in the oxygen. And now for the nucleophile, it is going to be CH3 because we know that magnesium and bromine go away. And I'm left with the actual active nucleophilic species. Now, what was the steps that we were doing before with the other reductions? What happens first? Beautiful. We do our nucleophilic attack to the partial positive, and then we have to kick up the electrons up towards the oxygen. So we're creating this little guy in here. And now notice I'm just attaching a carbon chain in this case. At this point, if we were using any of the other reagents, the sodium or lithium reagents, what would we add instead of a carbon chain? A hydrogen, exactly. So again, that's the main difference between normal reductions and Grignard's reductions. Okay, we have this guy. Now, is that it? Is that my product? How am I going to stabilize it? I'm going to protonate it with water, exactly. So at this point, my oxygen is just going to take away one of those hydrogens so it can get neutralized. And that's it. What kind of alcohol group did I just create? Tertiary. Were we able to create a tertiary alcohol with a sodium or lithium reagent? No. Again, that's another difference. Okay, so far, questions on that? So with the sodium and lithium reagent, those guys are gonna add a hydrogen and they only can create an alcohol up to a secondary degree. But with Grignard's, that guy is gonna be able to add a one extra carbon chain. So max, we're gonna be able to create something that's a tertiary alcohol. Okay, that's the main difference.
You said the sodium and the lithium create secondary.
Max, the secondary one. Yes, that's the max. Any other questions? We're good for the next one? Okay, now. This time, what kind of functional group are we starting with? Ester. Okay, so is the mechanism going to be the exact same? Yes or no? We have a leaving group in this case, exactly. Okay, so let's do the same exact thing. I have my dipole moment. I know that, whoops. Okay, I know that magnesium and bromine, they leave, and then F, what's that? Ethyl group, so that means how many carbons? 2, thank you. So let's just simplify it in here, which is the same as, whoops, that's a little too many. Okay. So same process. We do the nucleophilic attack, we kick up the electrons. And now we form our intermediate oxygen minus, and we just connected the 2 carbon chain. Okay, now what happens?
The double bond on the oxygen reforms with the second oxygen is displaced.
Exactly. Remember, the main difference was that now we have a leaving group. So that means that electrons go back down, and that's how we kick out our leaving group. So now what kind of functional group am I creating? What's the name? A ketone. And then technically your byproduct, it's still gonna be here. Okay, is that it? What do I have to do now? I have to do the nucleophilic attack once again, because remember, for reductions, we don't want any double bonds left over. So in this case, what nucleophile is gonna come back? The ethyl group, exactly. Ethyl just comes back again, attacks, and you kick up your electrons once again. And then you still have your little byproduct in here. Okay, and then to just stabilize everything, we know that, we just do an acid-base reaction. So both oxygens are just gonna take away one hydrogen, so we end up with this little guy. Plus your little byproduct in here. Okay. Questions on that? Yes.
Is the first step always
Yes, it's always the first, same exact thing.
second step? On that?
The double one came back because first of all, since we know that we have a leaving group, we need to be able to kick it at some point. So to do that, I'm gonna be taking one of those lone pairs in that oxygen to create again my pi bond in here. And to do that now, this carbon would have 5 bonds. So that's not possible. So that's how we're able to kick it out finally. So basically, I'm just shifting around my electrons. Yes.
Wait, you put like, is shouldn't it be H3O if both oxygens are taking one hydrogen and one hydrogen?
Do you mean as a byproduct or as a reagent?
No, H. The hydrogen.
Whoops, here.
Yeah.
It doesn't really matter. Yeah, very good. Okay, so far, questions on that? Now, pretty much we're doing the same exact mechanism as the previous session. Same exact thing. The only difference again is what you're connecting in there. For the previous one, it was just a hydrogen. This time, it's going to be a carbon chain. So we have 3 more practice problems. So for that, I'm going to ask for volunteers. But before that, I'm going to give you 2 minutes. Or do we have a volunteer? We have one? Okay, let's just start with it. You can choose whatever molecule you want. Go for it. Okay, that's better. Okay, this time we have a phenyl group. We do the nucleophilic attack, it gets connected there, beautiful. Then you have to reform your double bonds that you kick out your leaving group. So now we don't have anything that's cyclic at this point. We have a ketone, beautiful, and then we don't like that, so nucleophilic goes back again. Kick out the electrons. Okay, beautiful. So far we have 2 phenyl groups. So we don't have any more leaving groups or any more carbonyls. So now we just have to neutralize everything with water, exactly. So water is just gonna give us our little alcohol groups. Phenyl, phenyl, alcohol, your carbon chain, and alcohol at the very end. Great job. You absolutely got it. Okay, do we have questions on that? Yes. It's just a benzene group with a, do we have the marker in here? No. Yes, we do. Yeah. Can I have the iPad? But still, great job. You got it. Was she going a little fast? Yeah, okay. But don't worry, at some point, we're all gonna get to that level. But either way. Whoops, where's the pointer? Okay. So again, first step, I know my dipole moment is here. This is my electrophile. This is my nucleophile. My phenyl group is gonna do the attack, gets connected in here. We kick up the electrons. So that's how we end up with this first intermediate, right? So far, so good? Okay, now, this time, because I started with an ester, that means that I have a leaving group. So that means that the lone pairs in the oxygen are gonna go back down to reform my double bond. And then this carbon would have an excess in bonds. So that's how we're able to open up that chain. Again, I'm just breaking open this guy. Okay, that's why I end up with this guy in here. So far, questions? Does it make sense? Any confirmation? We're good? Okay. Okay, now we have a ketone, but again, we don't like any double bonds. So that means that your greenish region is gonna go once again, does the nucleophilic attack, gets connected in here, and then we kick up the electrons towards the oxygen. So now we created a molecule that doesn't have any double bonds or any leaving groups left over. So now everyone's happy. So we're just gonna neutralize it with whatever solvent you were provided with. Usually it's just gonna be water. But yeah, we just finished off with an acid-base reaction. And that's how we end up with two alcohol groups. One of them came from the carbonyl. This guy came from the carbonyl. And the other one came from the leaving group. And then remember, because it was a Grignard's reaction, we added two carbon chains, which in this case specifically, it was just phenyl groups. Did that make sense? Did I lose anyone in the process? We're good? Okay, next volunteer to try the next one. It should be easier because this time it's a ketone. No volunteers? Okay, volunteer. Now same process. This time it's just a methyl group. We do the nucleophilic attack. We get connected there. And then that's our little benzene. There we go. And we kicked up the electron so that oxygen has a negative charge. And now no leaving group, so we can just finish off with an acid-base reaction. So now I just have my tertiary alcohol group, and that's it. Great job. Questions on that? This one was easier to follow. Yes. Do you want to do the next one? Okay. And then we have a bigger molecule, but same process.
Yeah.
Same process. So the phenyl group, or in this case, we're just represented with an R, nucleophilic attack gets connected there, kick up the electrons. But because we have a leaving group, we reform it, kick out the leaving group, and we go back to our carbonyl, which now it's gonna be a ketone, exactly. Then my little byproduct is just gonna be, there we go, beautiful. And then exactly, Grignard's is gonna come back again, do the same steps. Nucleophilic attack, kick up the electrons. So now we don't have any double bonds or anything with a leaving group, so we're good. So now let's just make everyone happy with our acid-base reaction with water. they just take a little hydrogen and we end up with a little tertiary alcohol group and our little byproduct. So yeah, there we go. Great job. Great job. Okay, questions on that one? It was very similar to the previous one that we did. Yes. Okay, we don't need to expose anyone, but this one, the cyclic one? This guy in here. Oh, whoa, whoa, whoa. This one in here? I just wanted to point out where those oxygens are coming from. So the oxygen that's closer to the R groups that came from Grignards, that's where your carbonyl was. Because it's important for you to notice where they're coming from, because at some point we're going to do retrosynthesis problems. So you need to be able to identify where exactly they're coming from. Yes. That's just a preference that he wanted to make. That's completely okay. Like it's the same thing as just writing pH. Same exact thing. What? Let me zoom out so everyone can see everything. Can you see everything? Yeah. Okay, do we have questions so far? Do we need to go over any problems again? Do you need to go over the third one? You sure? We can go over it again. There's no problem with that.
Oh, come on.
Okay, whichever one it is. But actually, no, yeah, just for the sake of it, let's just go through it again. Because why not? It's not gonna hurt anyone. It's not gonna kill anyone. So again, same process. I start with a phenyl group. Again, that's just a benzene group. Magnesium and bromine go away. You're left with your negative charge. You do the nucleophilic attack, which means that you're connecting it over here. And then we kick up the electrons. Actually, let's start color coding. So maybe it's going to be easier to notice. Okay. And then this phenyl group is here. Okay. Now at this point, because we start with an ester, I have a leaving group. So I need to reform my double bond. So that's why, whoops, that's a little too much. Okay. That's why I take those electrons from the oxygen to go back down and reform a double bond over here. That's why this one now, it's blue. Okay, for you to notice where exactly they're coming from. So now we have a ketone, something different, but still something with a carbonyl group. So that means that your phenyl group is going to come once again. But again, let's just color code everything so we keep track of everything. So again, that oxygen that's hanging from the side, that was your leaving group, okay? This phenyl group that you see in the ketone, it came from the first nucleophilic attack, from the first time that we used Grignards. But now we know that the phenyl group is going to come once again, same process. Nucleophilic attack gets connected there. We kick up the electrons up towards the oxygen. So now I have the phenyl group from the second attack, the phenyl group from the first attack, and I still have the oxygen from the leaving group. So far, we're good? Make sense? Okay. Now, we don't have any more double bonds or anything with a leaving group, so we can just do our acid-base reaction with H2O. Exactly. That's it. No problem. Yes. So yeah, you always need to do the same process all over again whenever you reform a double bond. Okay, so I think the color coding helped a little bit. So questions on that? We're good? Okay, no. Let's go through a practice runs that you might see on the exam. Okay. Can someone show me the mechanism and the product for this guy? Volunteer. No reduction? What do you think? Volunteer, guys. Or do we do victims? Say that again? Brave soul that wants to give it a try. No one? Exactly. Now, first of all, you have to see what's given in the problem. We have a methyl group. That's going to be your greenness reagent. And then we have, what's the name of that functional group? Ester, beautiful. Do I have anything acidic in the molecule? Acidic. So what's going to happen? It's just going to be an acid-base reaction. So yeah, I'm just going to deprotonate it. So it's going to be the same exact molecule, which is going to take a little while to draw out. This is just going to be O minus, carbon chain, carbon chain. And then we're giving water. So what's going to happen now? So we go back to this same exact molecule. Yes, if we weren't given water, then yeah, it's going to stay as an O minus. But this case, yeah, it's going to go back to the same exact molecule. And then it gains it back and we get the same exact molecule. It's not a racemic in this case.
So it should.
We go back to the same exact thing. Again, this whole problem was just to testing your knowledge. Grignards can do a reduction, yes, but if you see anything acidic at any point in the molecule, you're not going to do it. You're just going to do an acid-base reaction, which is what happened in here. Because we know that magnesium and bromine go away. I'm left with the actual nucleophile / base. So the base is going to take away that hydrogen. And that's how we end up with oxygen and a negative charge in there. But then water is given again, so we go back to the same exact thing. Questions? Does it make sense? Yeah. We're good? Okay, no. Can you repeat why there's no reaction? Yes. So in this case, wait, okay. So there is a reaction, but it's not going to be a reduction per se. It's not going to happen because whenever you see anything acidic in the molecule at all, at any point, that means that you can do your reduction. The only exception is going to be whenever you're giving Grignards in excess. Okay, later on, we're probably going to see a problem on that. But for now, if you see anything acidic at all, you're not touching the carbonyl at all. You're just deprotonating. That's it. Okay, yes. Technically, yeah. It should be considered acidic, but I haven't seen BRH, but you get the gist. Yes. You got it. Okay, now let's see a slightly different question in here. Read it carefully. Again, remember all of your basic concepts. In this case, they're asking which of the following cannot form a Grignard. So again, be careful. B? D? Everyone thinks it's D? B? I hear both. Okay, so in this case, why did we choose D? Simple as that. This guy is the only one that has an alcohol group. Grignards is very, very picky. If you have anything acidic at all, it's not going to do a reduction. So yeah, it's going to be D. In option A, what functional group do you see? Ether. Yes. Okay, so again, this one is basically just getting used to condensed formula. Again, if you're not comfortable yet, please practice it. Just it's gonna stay until the final. We're good? We're good. Okay. Do we have any questions at all on reductions? Okay, let's do a quick conceptual quiz. How do I know I'm doing a reduction? What's the main change? Exactly. We're decreasing the amount of bonds between carbon and oxygen. How do we know we're doing an oxidation? Complete opposite. Exactly. Yes.
How would you go about it? Like, where the pH, would it affect the brownie?
This one is not doing a reduction per se. This one is not asking you to do any of the reactions that we just did in here. It's basically what we talked about in here, how to make your Grignards. We need to make the Grignards because none of the answer choices were a Grignard reagent. So we're trying to make it. So to do that, we need an alkyl halide. So we were like, all of them, yes, but D, because that's the only distractor. Yes, you got it. Okay, now, in lecture, did he talk about protecting groups? Yes, okay, we can continue then. Let's look at the next version in here. This time, we're gonna be talking about protecting groups. Now, when we talk about those guys, I like to classify them into different groups. Group 1 and group 2, simple as that. Now, from lecture, what's the basic gist with protecting groups? What do they do? Why do we use them? Exactly. It's all about basically just preserving the alcohol group. One group is going to retain the stereochemistry. The other one's going to flip it. What else? Nothing? From lecture? Nothing at all? Okay, that's okay. Let's work with it. Okay, so again, basically protecting groups, we're always going to be swapping our alcohol group for something else that's provided. Now, the first group, it's going to be this one, the one with pure halogens. Okay, from now on, I'm going to refer to them as group 1 for you to identify them. Now, group 1, the most common ones that you're going to see is PBr3 and SOCl2. That applies for both professors. They tend to use those two most of the time, but again, basic gist, whenever you use group 1 of protecting groups, we swap OH for whatever halogen was provided on the arrow. Okay, and now, next thing that you have to know, and very important thing conceptually, is that we flip the stereochemistry. Group 1, it always flips the stereochemistry. Why do we think it flips the stereochemistry? What kind of mechanism does that make? SN2, exactly. So for example, if on the exam you get a question saying, when you use SOCl2, what kind of mechanism does it follow? Your answer is going to be SN1, SN2, E2, or E1. The answer is SN2, always, okay? So far, questions with that? Make sense? Okay, now, the mechanism, it's quite long, so you don't have to worry about it. As long as you know the main transformation, you're good. And that applies for Dr. Roche as well. I know that he shows you the full mechanism and it's very confusing, but don't worry about it. You're good. Okay, now, but a question that you might get is, which alcohol is going to react most rapidly with PBr? Sorry, there's a typo. Just add a little 3 in there. PBr3. Okay. Now look at your answer choices. Which one do you think is going to be the answer and why? Why A? So yeah, this one is basically refreshing your memories from SN2. SN2, we know that it's a one-step reaction, and it prefers an electrophile, in this case the alcohol group, to be less sterically hindered. So less steric hindrance, the better it is. In this case, A was the answer. Because let's look at the degree of the alcohol group. What is it? Primary, secondary, tertiary? Primary. What about in option B? Primary as well. C? Last one? Tertiary. So we automatically can see that D is just never going to happen at all. It just can't happen with SN2. The rest of them, they are possible, yes. But if we're looking for the one that's going to be able to happen at the fastest rate, the less steric hindrance in the attacking site, the better it is. So secondary, we know that it's not going to be as good as primary, but the difference between A and B is that the next carbons that follow are, first one, this one, it's tertiary. This one, it's secondary. So there's less steric hindrance in option A than B. Okay, so far, questions on that? It's basically just testing you on if you know SN2 or not. Yes.
Like the stereo SN2, which is the one. So if it was to ask like the lowest, it would,
D would not happen at all.
no, B.
B, the slowest one would be C. Mhm. But if you were asked to rank them, it would be A, B, and C, from fastest to slowest. But either way, we were talking about the purpose of protecting groups. And like you mentioned, it was to preserve or alter the stereochemistry. Now, something else that I want you to notice is that, okay, we use our protecting groups. We swap OH for a halogen, which means that we're creating our dear alkyl halide. Now, remember, alkyl halides, they have a good leaving group, okay? So something else that you have to notice for protecting groups for both group 1 and group 2 is that they form a good leaving group. Now, that could be relevant for a multi-step synthesis, because what if we try to do a substitution reaction afterwards? You have a leaving group, so you can proceed with it. Now, let's look at the next two. Tosylate and mesylate. Those guys, we're going to call them just group 2. For Dr. Roche, I know that he includes one more, which he just refers to it as TF. I forgot the full name, but you don't have to trifluoro something. But yeah, either way, they all fall under the same category, but for West, just worry about tosylate and mesylate, okay? Now, Dr. West sometimes likes to ask you which one is tosylate, which one is mesylate, which should be an easy point. But in this case, let's just review them. Now, for all three of those reagents, they have something in common, which is going to be a sulfur group that is double bonded to an oxygen twice. Okay, that's going to be the main thing that you're going to notice. But the one that has a ring, this guy is going to be tosylate. The one that doesn't have a ring is just your mesylate. And then for Dr. Roche TF, it's the one that has fluorines. Okay. So again, this is basically just identifying your reagents. Question on the right side. Say that again. Tosylate and mesylate is just the name of the reagents. So yeah. It's just a short name for this whole molecule. So yeah. Tosylate has a ring, mesylate doesn't have a ring. A mnemonic that I used last semester is that tosylate is a married gal, so she has a ring. Mesylate is a single gal, so she doesn't have a ring. Then for TF, it's just fluorines. So yeah. But now I want you to notice that main difference is that, yes, I'm still gonna swap my OH for something else, but this time specifically, I'm gonna be retaining my oxygen. I'm just swapping out my hydrogen, okay? I'm swapping out the hydrogen for whatever reagent I was given. So it's gonna be OTS in this case, for example, because we can draw the same exact molecule as this. I can just write OTS, okay? They both represent the same exact thing. And then same process for mesylate. I just take away my hydrogen and put whatever I was given on the arrow as my reagent. So this case is going to be OMS. Okay, that's it. And now, next important factor for you to notice is that I'm retaining the stereochemistry. Okay, so that's the main difference between group 1 and group 2. Group 1 flips the stereochemistry. Group 2 retains the stereochemistry. So let's just write this here. This one is technically not going to be SN2 because SN2 is going to flip your stereochemistry. But again, the full mechanism of group 2 reagents, it's quite long. At some point, you do have an SN2 step, but don't worry about it. you're gonna get yourself more confused with that. So easy to memorize, SN, whoops. Group 1 follows SN2, so it flips stereochemistry. Group 2, tosylate and mesylate, they don't follow SN2, so we can retain the stereochemistry. So far, questions on that? Yes.
You say the top part,
They're two different groups. Yes, they're two different things. They're two different groups, but they're the same kind of reagents.
you didn't do a reaction.
For group 1, we did do a reaction in here. This is just a generalized reaction. It's just for you to simplify the stereochemistry. We're gonna do practice problems next, so don't worry. Trifluoromethyl something, but yeah, it's the full shebang. So yeah, you don't have to worry about it. Plus that's for Dr. Roche, not for Dr. West. But let's look at this guy. Now, since you know that your professor, Dr. West, loves to show you the molecules in condensed formula, sometimes you're gonna get it like this. Now, it's not easy to identify that that guy is gonna be tosylate, for example, but something that he's always gonna provide is that he's literally gonna tell you what molecule it was right after it. Tosylate, there we go. So we know that tosylate is my reagent. So what's gonna happen to the molecule? The stereochemistry stays the same, so let me just start drawing out the same exact molecule. And then I have my oxygen with TS now instead of OH. Simple as that. Okay, now this is a multi-step synthesis, so I have OTS and then sodium with iodine. What's that? What kind of reaction are you trying to do? SN2, exactly, because remember, this guy, it's a pretty good leaving group. Sodium goes away and I'm left with a pretty good nucleophile. So we do SN2, which means we do the backside attack, which means that we flip the stereochemistry and then we kick out our leaving group. So that means that now I have a little wedge and an iodine. And then what about the methyl group here at the bottom? Do I change it? Stays the same. Why does it stay the same? You don't touch it, exactly. You don't touch it, you keep it the same. Do not mess around with it. So that's it. Okay, so far, questions on that? Does that make sense? We're good? So did we run out of time? We did run out of time. So we're gonna continue with our discussion on Friday. Remember, the session is gonna be in SO 270. It's not this building, so please don't confuse it. And it's at 11, it's not at 1. Oh, yes.
So here, why is it 3-2-1 and then it was like the other one was like 3-1-2?
That's because your Dr. Roche and Dr. West, they differ on the ranking, which is a little silly and very confusing for students, but you just worry about 3, 2, 1.
Okay, and then
That's it. Just worry about that.
why was this in addition instead of
So that's your. You start with a haloform reaction.
Mhm.
And then you continue with your West reaction. It's not a thin addition per se, but we know that in the West reaction with some ether synthesis, once the oxygen attacks the carbon with whatever halogen you were given, that's an SN2 attack.
Mhm.
So we flip the stereochemistry. So in this case, they shouldn't be the same.
shouldn't those like one be like that and then the other one like one should be bold and one should be dashed?
Yeah.
Okay, because on the answer that I saw it was like that and I was confused.
Let me double check for you. He was trying to show you the same thing, but this is what I have on my answer. First one is just your, sorry, halohydrin formation.
Mhm.
This guy creates a trans product. It's gonna be the OH and the chlorine,
That's fine.
and then we continue with our West reaction. So we deprotonate alcohol, and then we do our nucleophilic attack, SN2 specifically, so we flip.
The seals will add on the same side.
On the first step, that's gonna be your intermediate between here. So whenever the two chlorines are on that step, they're gonna be on the same side. But then, once you wanna switch it, one of them for the OH,
I thought they added on the opposite side because.
no, they don't do, because
Okay.
overall, this is an anti-addition. So
Okay.
that's why these guys need to be trans to each other. So yeah. You can look back on your chapter 8 notes,
Yes, ma'am.
look for specifically for this reaction, halohydrin formation, that's the name,
Okay, thank you.
no problem. Yes. Let me just stop this recording. Go.